This last section is just basically going to summarize everything that we have learned about least squares, regression line, and linear models. So regressing, the least squares regression line can be calculated 2 different ways. One is using your calculator, and that's pretty straightforward. Once you have your x is, or put into list 1, for example, and your y is put into list 2, you're going to go ahead and hit Stat, Calc, scroll down to 8, which is the least squares regression line, and then you need to, it automatically uses list 1 and list 2 for your explanatory and response variable. And then if you want to store it, you have to tell the computer that, and I'm going to give you information on that in class, so you'll have that in front of you. The other way to calculate it is to calculate your slope, your b. Your b is this y hat equals a plus bx. Why it's opposite, the way you learned it in algebra, I don't know. But the slope is going to be your R correlation coefficient times the standard deviation of y divided by the standard deviation of x. On the test, in this, the AP test and the test that we give you, those values will be given to you. You don't have to calculate them. You just have to know how to put them into the formula. And remember, this formula is on your formula sheet. This formula is on your formula sheet, so you might want to annotate that on your own formula sheet so you have a remember of what it is. And then the y-intercept is just the mean of the y's minus the slope times the mean of the x's. So remember, y bar and x bar are the means. Okay, when we start looking to see if there's an association between an explanatory and a response variable, and we think that there is a linear association, then we can go ahead and create a least squares regression line. The least squares regression line is an ideal line that is created by minimizing the sum of the squares of the residuals. So on each residual, we want the squares of the residuals, the sum of all of these, to be as small as possible. And the calculator does that for us, so we don't have to worry about calculating that, but we need to recognize that there is one ideal line, and that is created by the sum of the squares of residuals. The least squares regression line, by the way, will always go through the average, the mean of x and the mean of y. So let's say the average, the mean of x was here, and then the mean of y was there. The least squares regression line will always go through that. When we decide that there is a linear association, we know that we can talk about how strong and the direction of that association by looking at the R correlation. The calculator will do that for you. We'll make sure that your calculator is set to be on to have that R. If you don't have it though, and it just gives you the R squared, you can go ahead and find the square root of R squared, and that will give you the value for R, and then from there, of course, you have to look to see approximately 0.815, and obviously this one is heading in a negative direction, so you have to pay attention to the direction. But the R gives you both the strength and the direction of the correlation. This one's pretty strong in the negative direction because it's getting close to -1, which is as strong as you could possibly get in a negative direction, be a perfect linear negative association, whereas +1 is perfect line going up in that direction. An R will never be bigger than 1 or less than -1. It'll be somewhere in between, and we only use it with linear models. Also a big deal, and you will have questions on the test that test your understanding of this. An R has no units. It's just a metric of strength. So that when we're talking about our linear model, we want to know how strong it is, how good it is. And so we have 2 metrics for that. And one is the S, and the S is the standard deviation of the residuals. And so remember, the residuals are the errors in the model. They're the original data. But if we're looking at the strength of our model, we don't want the standard deviation of the error of residuals to be that far off. So it's telling you the typical distance from the model, and it has units. So we're looking at S in this case is not miles driven, price in dollars, and that standard deviation is off by almost $6,000. So since our data is like 7,000 to, I don't know, like $43,000, to be off by almost $6,000 seems like a pretty loose model. The second thing we can look at is the R squared, and the R squared talks about the variance that can be attributed to the model itself, the percent of the variance. So obviously the higher the percentage, the stronger the model. This one has a 66.4%. And to interpret it, you pretty much want to just memorize this statement. And so we would go ahead and, looking at this, we would say about 66.4% of the variation in price is explained by the linear model relating miles driven to price. 66.4% is not really that strong of a model, since 43% is not explained by the model. So this is just an okay model. One of the things you need to be really careful with is that we have focused almost exclusively on linear models, and so remember that correlation and regression lines only describe linear relationships. So we can't use R to talk about the strength of this one. I mean, you wouldn't use a linear model because obviously it has a curve, and this one is not linear either. It's got a vertical thing and then some weird outlier. So both of these we should not use R to talk about how strong it is, or a regression line to allow us, because even though the least squares regression lines for both of these are exactly the same, it's inappropriate to use them. Now this one and this one, this outlier radically affects the R correlation coefficient. So even though they have the exact same least squares regression line and the exact same R, we know if we took this one out, the R would be much, much stronger, and we might still start with 3, but our slope would be smaller. So this brings us to the fact that also that outliers can radically affect the least squares regression line and the R. Here we're going to talk about outliers, and I want to remind you, because you're going to have to get this memorized and keep it memorized. When we have outliers in single variable data, we have ways of deciding if they actually count as outliers, and that's, we look at the Q1 minus 1.5, the IQR, or we put Q3 plus 1.5, the IQR, and if something is beyond that, above this, it's considered an outlier. Beyond that, below that, Q1 minus 1.5 IQR, it's considered an outlier. Now, there's no metric, there's no measurement or calculation that we make to decide if a point is an outlier on a scatter plot. But we can look at its effect by taking it out from a set of data to see what's going on. So this particular graph that we're looking at talks about the age of first word months and this adaptive scale that I'm not sure if it has to do with their, I'm not exactly sure, but there's a correlation with all 19 kids. Remember, N stands for the number of individuals in a sample. And with all 19 kids, we have a R of negative 0.64. It's clearly a negative it's a negative association, fairly, it's medium strong. And then the slope here says that the adaptive scale goes down 1.17 marks for every month later that a child might say their first word. Now we have two outliers here, child 19 and child 18. We're going to first talk about child 19. Now when we take child 19 out, who's an outlier on the Y, then the correlation coefficient of R gets stronger because the points are tighter and closer together. So by taking out an outlier that is on the Y, you're going to probably increase the strength of the correlation and increase the effect of that. So there's a higher score on the adaptive scale for every month. Without child 18, on the other hand, this guy or gal, they didn't start talking first word till they were a little almost 3.5. So by taking that kid out, the cluster of data is way more like that and less of a line. So the R becomes much weaker, and the slope gets weaker as well. But by an X outlier often affects the R strongly and affects the least squares regression line. So when we talk about things that are not resistant, correlation is not resistant, least squares regression lines are not resistant, and back to the old things, mean is not resistant, standard deviation is not resistant to outliers, IQR and median and stuff like that is. But remember, correlation and least squares regression lines are not resistant. This pretty much sums up what I just said, so you can go ahead and read it. Probably said it better than I did. There you go.